Welcome to AI Frontiers. Today's episode explores a remarkable snapshot of progress in robotics. We examine 19 groundbreaking papers, all published on the arXiv preprint server within a single 24-hour period, from December 13 to 14, 2025. This collection spans humanoid recovery, semantic navigation, and the profound integration of artificial intelligence, control theory, and perception, charting the future of embodied intelligence. This presentation will journey through those 19 robotics papers from that single day. It will uncover the dominant research themes and methodologies that are currently driving the field forward. We will explore specific breakthrough papers with significant real-world impact, understand where robotics research is heading next, and see how the strategic integration of different approaches is propelling modern robotics forward. Robotics is the integrative discipline where artificial intelligence algorithms meet physical systems. It creates embodied intelligence, systems that can perceive their environment and execute physical actions to change it. This field transforms industries, from manufacturing to space exploration, by solving the immense challenge of operating reliably in complex, real-world environments. It effectively bridges digital intelligence with analog reality. A dominant research theme is integration and hybridization. This involves combining the strengths of different methodologies to create robust solutions. For instance, model predictive control is used to safely guide the trial and error process of reinforcement learning. Planning frameworks chain together simple models for long-range strategy with complex models for precise execution. This fusion of classical control theory with adaptive machine learning allows each component to compensate for the other's weaknesses, acknowledging that real-world complexity demands multiple complementary approaches. The second major theme is generalization and adaptability, which focuses on escaping the brittle robot problem. Research aims to create single control policies that can operate diverse robot morphologies and systems that understand commands given across different modalities, like speech or gesture. New evaluation frameworks test how artificial intelligence handles completely unexpected scenarios. The goal is for robots to adapt to new tasks and environments without requiring extensive reprogramming, moving beyond lab-perfect performance to real-world robustness. The third critical theme is perception and representation, which concerns building useful internal world models. This goes beyond processing pixels to creating actionable understanding. Approaches include using vision language models to ground semantic concepts in three-dimensional space, creating hybrid datasets that blend real and simulated sensor data for better algorithm training, and employing multimodal sensor fusion, such as combining visible light with thermal cameras, for navigation in challenging environments like dark asteroids. The quest is for semantically rich and robust perception systems. Key findings from the day's research include several significant breakthroughs. One demonstrates zero-shot morphological generalization, where a single reinforcement learning policy successfully controlled 7 different humanoid robots with varying proportions. Another shows model chaining, which improved aggressive flight path tracking for a drone by 75%. A third finding is structured affordance grounding, which elegantly abstracts the question of where to act from the how to act. A fourth is a conflict-aware heuristic for multi-agent planning, yielding a 2.5 times speedup. Each finding addresses a fundamental challenge in robotics. These advances are powered by a sophisticated toolkit of methodologies. Model predictive control provides safety guarantees through constraint-aware online optimization. Deep reinforcement learning enables robots to discover complex behaviors through trial and error in simulation. Bayesian optimization allows for efficient, sample-efficient tuning of parameters on real hardware. Probabilistic state estimation, like Monte Carlo localization, provides robust handling of sensor and positional uncertainty. Finally, foundation models, particularly large vision language models, contribute common-sense semantic understanding of scenes and instructions. The first selected paper is MPC-guided Safe Reinforcement Learning and Lipschitz-based Filtering for Structured Nonlinear Systems by Kostelac and colleagues. This work unifies the adaptive power of reinforcement learning with the safety guarantees of model predictive control. During training, the MPC acts as a guardian, defining a safe control envelope within which the RL agent can learn. For deployment, A lightweight safety filter validates the learned policy's actions. Tested on a nonlinear aeroelastic wing system, this hybrid approach provides a formal framework for deploying adaptive autonomy in safety-critical domains. The second seminal paper is SAGA, Open-World Mobile Manipulation via Structured Affordance Grounding, by Fang and team. It breaks down the problem of instruction following by separating the what from the how. Foundation models are used to ground user commands, whether language, gesture, or video, into a three-dimensional affordance heat map in the robot's camera view. This heat map highlights where action-relevant parts are, like a drawer handle. A separate policy then learns the motor skills conditioned on this consistent spatial representation. Tested on a quadrupedal mobile manipulator across 11 diverse tasks, it enables zero-shot generalization and presents an architectural pattern for generalist robots. The third deep dive is into VLG-Loc, Vision Language Global Localization from Labeled Footprint Maps by Aoki and collaborators. This paper solves global localization using simple, labeled maps instead of precise geometric scans. A vision language model analyzes a panoramic image to probabilistically detect semantic landmarks listed on the map, like cashier or entrance. These detections are then fused using a Monte Carlo localization framework to estimate the robot's pose. This method proved more robust to environmental changes, such as rearranged store displays, than traditional laser-based methods, significantly lowering the deployment barrier by utilizing human-readable maps. Future directions for robotics research are clearly indicated. A primary challenge is closing the simulation-to-reality gap with more accurate physics models and robust training paradigms. The field will see development of robotic-specific foundation models trained on physical interaction data. Computational efficiency for edge deployment on mobile platforms is critical, driving research into specialized hardware and efficient algorithms. Enabling continual and lifelong learning for long-term autonomy and creating better benchmarks to test generalization, robustness, and safety in diverse scenarios are also key frontiers. This presentation was created through AI synthesis and expert review. The narrative content was synthesized using a large language model. Text-to-speech synthesis was performed via Google's technology. Image generation capabilities were provided by OpenAI. A human expert reviewed the final material for accuracy and coherence. It is important to note that some oversights may exist despite this review process. To stay on the cutting edge of artificial intelligence and robotics, subscribe to AI Frontiers. Get daily, clear breakdowns of emerging research to understand complex developments. Join a community of enthusiasts and experts to never miss a breakthrough in these rapidly advancing fields. In conclusion, the research from this single day highlights key takeaways for the integrated future of robotics. We are in an era defined by combining methods, ensuring safety, enabling adaptability, and achieving understanding. Generalization has become the new benchmark for success. The field is focused on bridging to the real world through advances in computational efficiency and safety guarantees. Foundation models are being effectively utilized as powerful semantic sensors within larger systems. Robotics is demonstrably progressing from specialized, single-task capabilities toward more generalist intelligence. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.